the father, if you will, of a J2 model, and then go into some more details of a J2 model, like allowing it to harden. So very quickly, I don't want to spend too much time on a Tresca model because it's kind of an outdated model. What the Tresca model says is that if you order principal stresses in this way, so that this is your maximum tensile stress, and this is your minimum or minor. Okay, here I mean tensile, but it could be negative as well. It just simply means that positive, we'll take positive as tensile, and negative will be compressive. Okay, so sigma 1 will always be the maximum tensile stress or the least compressive stress, you know, in that order. Okay, you just put them in order. Okay, so this is a sorted list. Okay, and this is of course the intermediate. Okay, so the failure or yield criterion they really originated as failure criteria. Then later people realized that, okay, they could generalize the notion and just make it plasticity. But at the beginning, it was a failure criterion that essentially says that, that failure is achieved when the difference between the two extreme principal stresses is equal to some value that here I'm calling capital Y. Okay, and if you remember your Mohr circle stuff, right? You remember that, how is it that there are two circles, right? There's like sigma 3 bar, sigma 2 bar, and then there's another circle between sigma 1 bar, let's say, and sigma 3 bar, right? You remember this stuff from your mechanics, right? So what this failure criterion is saying, and many others, is that this difference is the one that matters. And when you get to a certain value, in this case, the value of the diameter, right, which in this case would be half of this radius, right? So this would be y over 2, this height, right? That's the radius. Failure is achieved. Okay? So it's very simple. It just says failure happens when you're pulling too much in relationship to how much you're pulling in the minor stress. Okay? So this is, of course, independent of sigma bar 2. So sigma bar 2 can be 0, whatever. It doesn't matter. According to this yield criterion, or this failure criterion, the only thing that matters is the difference between the two principal stresses. Okay? This is what's called as the Tresca model. And since we have a sigma 1, sigma 2, sigma 3, three principal stresses always that come from your general state of stress, and they can be in any order, you can have, right, three choices for what we're calling here sigma bar 1. Right? So either one of these can be sigma bar 1, because when you get the principal stresses from sigma, you don't know in which order they are. They're just three different numbers. Okay? So this could be 1, this could be 5, this could be 10. In which case, sigma 3 will be sigma bar 1. Okay, in the sorted order list, sigma 1 bar is the greatest of these three. Okay, so you have three choices for sigma 1. And then for each one of the three choices, you have two choices of which one is going to be the corresponding sigma 3 bar. See what I mean? So sigma 1 could be the sigma 1 bar, and then sigma 2 could be the sigma 3 bar. That should be equal to some constant, right? Well, in fact, let's just call it what it is, 1. Okay? Sigma 1 could be the sigma 1 bar, and sigma 3 could be the sigma 3 bar. Okay, that's the other possibility. Then sigma 2 could be sigma 1 bar. And do I take into account sigma 1? Yeah. Sigma 1 could be sigma 3 bar. Sigma 2 minus sigma 3 could be another possibility. Sigma 3 minus sigma 1. And finally, sigma 3 minus sigma 2 is the other possibility. 6 possibilities. 3 times 2 possibilities. Come on. For, say, yield or failure. And you have to check for all 6 of them, essentially. Or you put them in order and then you check. All right, so in the pipeline, might as well use the ruler. So, thank you, Alex, for getting this. So in the pipeline, let's a bit more up. Will look like this. So here's sigma 1, here's sigma 2, here's sigma 3, or let's be consistent. I think I've been using sigma 1, sigma 2, sigma 3 for this. It doesn't really matter. So you can check that each one of these guys will give you a plane on the deviatoric view, okay? And that plane kind of looks like this. Again, the way to see those planes, and I invite you to do that, is to remember when we did the rotations? Okay, they were done for a reason. The rotations enable you, remember we were calling this guy, I think, sigma 1 double prime. This is sigma 2 double prime. Convert all of these guys, the J2, the Tresca model in principal stresses, convert them to the rotated axis and plot things out, okay? And you will see what I'm about to draw, okay? But, okay, I won't spend time here doing that. I'll just give you the end result, but I expect you guys to be curious enough to go back home and say, okay, why did he say that? Why is that the case? Okay. So the way this plots is that there's going to be a certain distance here. So the J2 model on this plane, I'm just going to sketch it, would give us a circle, right? That's what we did before, right? The J2 model essentially gives us a nice, beautiful circle here, centered at the origin. So let's see. This would be the J2 model. Right? We already saw that. Right? It's a cylinder centered at the hydrostatic axis. Here's the sigma 3 double prime pointing at you. The Tresca model shares the same intersection points as the J2 model does with the principal axes. okay? But instead of having this smooth circular form, it has straight planes, straight edges in between. So that's one edge. Okay. Here's another edge. Is that right? Yeah. Here's another edge. Here's the other one. Here's the other one. Here's the other. It's a hexagon. It's been a bit distorted. It's a hexagon. This is Tresca. So this is a circle on this plane. This is a hexagon. Okay. Further introducing nomenclature. From now on, we're going to call this kind of intersection a tensile corner. So these 3 points where my yield surface intersects the positive value of the principal stress axes, those are going to be tensile corners, okay? So let's say in the absence of sigma 1 and sigma 2, if we had a value of sigma 3 being 3 pascals here, that would be a tensile corner. As opposed to its negative side, which we are going to call a compressive corner. And you will see later why we make that distinction. In this particular case, what these yield stresses, or what these yield criteria are telling us, J2 or Tresca, is that materials yield or fail equally in tension or in compression. They don't make any distinction between the 2 states. But there will be materials where you have more strength in one direction than in the other, right? For instance, concrete, it's a lot more strong. It's a lot stronger in compression than in tension, right? So the intersection with the tensile value of the principal stresses might be shorter than the one for the compressive stress. Okay. So things will get distorted later on. But for now, that's the way it looks. Questions? No? Okay, so immediately should jump at you that Y, this capital Y, should be related to kappa. And they should be related to sigma Y. Okay? There's no way that they cannot be related. But I hope that you develop that curiosity to find out what that relationship is. I'm going to give you some answers, but you need to get there. Okay, so in 1D, as we said before, a state of tension or in compression is very straightforward to understand. In multi-D, tension and compression are more complicated. For instance, take this little cube of material. And let's suppose that we're applying a principal stress sigma 1 here and a principal stress sigma 3 here, and let's say sigma 2 is 0. Okay? And they're both in tension. So it's like having this cage, and I'm pulling from this end, and I'm pulling from this other end, and nothing is happening on the plane. There's no sigma 2. Is that a state of tension or a state of compression? Say they're the same. Let's make it even simpler. Let's say sigma 1 equals sigma 3 equals some sigma. Biaxial pulling. What does your gut feeling tell you? It's tension or compression? Don't be shy. Yeah, I mean, there's nothing that makes you think compression, right? I mean, you're pulling in all directions except for one where you're not doing anything. So if I were to guess and say, what state is this material in? I'd say tension. Okay, check what this says. So the line of sigma 1 equal to sigma 3 happens to be exactly this line as well. Okay, projected on this plane. So you are really, when you are at a sigma 1 equals sigma 3 state, like that, you're walking along a line like this. And if you were to fail, you will actually fail the material in compression. Okay? You wouldn't fail it in tension. That state, that three-dimensional state of stress is not a state of tension, it's a state of compression in the way that we have defined it here. In fact, you can show that it is analogous to having a pure state of compression if you cook it up the right way. It's similar to having a sigma 2 negative and nothing else. Okay? But, so you need to be careful with your states of stress in 3D. That's why you need to project them onto either dilatoric planes, hydrostatic planes, so that you can see what's going on. And you can no longer jump into conclusions like, oh, tension, compression, that easily, that quickly. Or loading, unloading. You know, the fact that one of them might be dropping doesn't mean that you have unloading. The other two could be increasing, and so on. Okay? You can no longer conclude that you have softening or hardening as easily as before. Okay? So just be very aware of it. There will be a relationship between Y and kappa, and that relationship is that Y is the square root of 3/2 of kappa. Okay, and this makes, just as above, the corners of the Tresca model match the Mrs. circle. Okay, just like this. So when you set Y equal to 2/3 square root of 2/3 kappa, you get what I just pictured here. Okay, you get the circle of Tresca to inscribe, or is it inscribe or circumscribe the Tresca model? I always confuse the two. One is inside, the other one is outside. Whatever. You see what I mean? Okay. The Tresca surface is inside of a J2 or the Mises surface, and the corners of a Tresca intersect the circle of the J2. When Y equals 2/3 square root of 2/3 kappa. That's the only time they consider. Please check this.
That's 3 columns.
Huh?
It's 2/3, right?
Oh no, it's 3 halves.
Oh, 3 halves.
Okay. So I'm saying something else?
2/3.
No, it's 3 halves. It's what I wrote.
Well, yeah.
Okay, check it please. So again, the way to check it is to take J2 to the rotated axis, to take Tresca to the rotated axis, okay? And then check that that's the case. Okay? I think there's an exercise in Borja's book that actually makes you do that. So just check it out. Okay, that was the father of the J2 model, the Tresca model. This is a generalization that is a smoother version. It's much more preferred because it doesn't have the issues at the corners. Okay, you can see that if you happen to land at a corner, you're going to have many issues, like you don't know how to compute the normal right, at that point. So the use of J2 really essentially replaced completely the Tresca model, but the first one was the Tresca model.
I have a question way back here.
Yeah.
When you said there are 6 possibilities for yield of failure, what did you mean by that exactly?
That each one of these guys, it's one of these equations.
Okay, but I thought only sigma 1 bar and sigma 3 bar mattered.
That's right, but you don't know which one of these 3 is going to be that. And at one particular moment in time, sigma 1 and sigma 3 might be the guys that matter. But then later in time, as the state of stress changes, it might be sigma 2 and sigma 1, right? So you might come and hit this plane at some point, and later on come and hit that plane. Yeah, from an ordered point of view, there's only one plane, which is pretty much this one. But in a general stress space, it could be anything. It could be any of the 6. That's what I mean. Yes.
I have a question about the compression state,
yes.
Specifically for your example, because I'm imagining that sigma 2 in this case is 0. And so
is.
I just do a simple Mohr circle picture in my head, and there's no stress state that's compressive through any rotation.
No.
Because everything's going to be right to the... So then why is it called a compressive state if there's...
Because you're hitting a compressive corner.
So how does that compressive corner relate then to compressive stress states? Or does it have any relationship to them?
To the one-dimensional one, no.
Okay.
There's no, I don't think you can work out I don't think you can go from a 2-dimensional or 3-dimensional state of stress to a 1-dimensional equivalent state of stress. If that was true, we wouldn't do multi-D plasticity, right? We would always boil it down to some 1D, right? And we just can't do that. Yeah.
Well, in this specific case, it kind of seems to me like if you set your base at the hydrostatic, on the hydrostatic axis where everything is sigma, and then you like remove the sigma in the sigma 2 direction, then you're sort of applying a negative sigma 2. Does that make sense?
So say that again?
So let's say you start that cube with in hydrostatic axis at sigma 1 equals sigma 2 equals sigma 3 equals sigma, I guess.
Okay.
And then you apply a compressive negative sigma in the sigma 2 direction.
Okay.
That's sort of how you end up there. With the
Yeah,
sigma, right?
yeah, right.
So I can kind of see where it comes from, I guess, in that sense. You base everything from the hydrostatic axis.
So let's see if I understand it. So, but that's a different state than the one we have here, right? So you would start at a hydrostatic state with some value of sigma, right, for all 3 of them.
Mm-hmm.
And then you say, okay, I'm going to keep sigma 1 and sigma 3 constant at sigma.
Yeah.
And I'm going to further increase sigma 2 in the negative direction.
Yeah. So
Oh, absolutely. And you would make a path just like this.
Yeah.
I see that. Right. So, but then this one, let's say, what kind of path does that follow? Let's see, if you keep, so that one, let's say you start everybody at 0, and then you keep sigma 2 at 0, and you keep pulling from sigma 1 and sigma 3, let's say, with the same amount. That's not quite, it doesn't originate at the hydrostatic axis. It kind of goes like this, right? But, yeah. So it's, but the projection of the 2 paths on the pi plane they look identical. You see that? And in fact, both of them will hit that edge. So imagine that this is a hexagon, just like a cylinder, but instead of a cylindrical cross section, you have a hexagonal cross section. Both of those stress paths, the one you're describing and the one I'm describing, they're both going to hit that edge that comes out of the page, exactly there. Okay.
But he's saying basically works, because if you are pulling in the 3 directions,
yes,
sigma 1, sigma 2, sigma 3 equal to sigma,
yes,
hydrostatic axis, pulling it. And then you unload sigma 2
yes,
from sigma to 0, you're basically compressing it. Right?
That's
You're
right.
going from positive to more negative. You're
Yes,
basically
that's right.
compressing it.
That's right. Yeah, that's another state that you would think. So let's say, yeah, you go to some arbitrary value in sigma that is hydrostatic out of a page, say out here. And then, yeah, you say, I'm going to unload sigma 2.
Yeah.
You would expect that still to be a state of tensile stress somehow, right? Because all you're doing is unloading one. You're actually helping the material by releasing one of its sigmas. And you're actually compressing the material. You see that? So you need to be very careful with these generalizations of tensile, compressive, unloading. You would think that that's an unloading state. It's not. It's a state of loading. It's a state of loading that will actually get you to fail.
It's pretty counterintuitive.
It is. So that's why you need to be careful in 3D with what you say and how you interpret things, because they are not as intuitive as they are in 1D. In 1D, yeah, you pull, you decrease, it's very intuitive. But in 3D, it could be tricky.
So one quick thing just to follow on. So I'm still imagining, so I have sigma 1, sigma 3, and then some sigma 2. I apply any rotation, acceptable rotation of the three-dimensional stress block brick. And no matter what rotation I'd apply, none of the sigmas I would get would be negative.
No, you cannot. In fact, these are invariants, right? So it doesn't matter what rotations you apply. You get always the same values. So there's no way out. I mean, there's no operation that gets you out of that state of stress to some equivalent.
Yeah, no, but none of them. So I can rotate it out of the principal stress state to some other stress state, and none of those sigmas would ever be negative to be compressive. They'd always still be tensile.
So I'm trying to understand what you're thinking. So you're trying to figure out if there is a different state of stress, of principal stresses, that will land you at the same point, but with perhaps negative values of stress.
I guess I'm just confused as why it's called compressive, because if I imagine I draw a Mohr circle of sigma 1, sigma 2, and sigma 3,
yes,
they all have to be in the positive.
They don't
sigma.
have to be. They happen to be in this particular
Yeah, so in this case.
In this case, but you could have, for instance, I drew here on purpose a sigma 3, for instance, that is negative.
Yeah, no, yeah.
Sigma bar 3. So they don't have to be.
Yeah, no, I agree. But in that case that you drew, they do happen to all be there.
This one,
and
yes.
it fails in a compressive state.
But
there's not a stress
by definition.
compressive. Okay.
By definition.
Oh, by definition. Okay, so
By
it's
definition,
just a definition. Okay.
Which is the same. That's why I said that you would land at the same corner if you kept sigma 1 and sigma 3 equal to 0, and all you had was a negative sigma 2. You would land right here again. So that's a one-dimensional state of stress that you would recognize as compressive in your usual way, and it lands right here. So if you want to understand in the usual way these corners, that's the state of stress that I imagine. I say, okay, everybody else, let's take this one. This one here in the traditional way, you can arrive here if sigma 3 is 0, sigma 2 is 0, and you have a minus sigma 1 that is compressed, or a sigma 1 that is compressive. You will land here, right? In the traditional, this would be this case, right? It would arrive here. So each one of these can be arrived at with your usual 1D compressive state. The same for the tensile corners, but in the opposite direction. Now, what I'm saying is that in 3D, you can arrive at exactly the same corners, but with a lot more complex combinations of stress, positive, negative, 0, whatever, that you, in your intuitive way, may associate with, for instance, you associate this one with a state of tension, when it's really landing you at a state of compression, exactly the same corner as you would get with this state.
The model is telling you that the state of stress doesn't depend on the sign in general, right?
That's also true, yeah. because what really matters is this relative distance between one and the other. That further introduces new nomenclature. Okay, play with Tresca, play with J2, play in these two-dimensional states. And then something that we haven't really talked much about in multi-D has been this concept of hardening and softening. Right? We introduced it in 1D, but then we kind of dropped it. So I think that the right time to pick it up again has come. So far, we are looking at snapshots of sizes of yield surfaces or failure surfaces that have Y or kappa constant. But in reality, this will be changing as a function of the loading. But at any state of stress or at any point in time, you can always take a snapshot of a material response, and there's always going to be a Y or a kappa present. Okay, so these are accurate representations, just they won't be constant in time necessarily. Right? So there are two types of formulations that people usually follow. The first one is called work hardening. And the second one, and the most utilized one, is called strain hardening. And here we're always going to use hardening in the general way, meaning that it could be positive hardening or negative hardening, meaning softening. Okay? So in the work hardening, kappa in the case of a J2 or any plastic internal variable increases or decreases with plastic work. And we will more formally define what that is in a second. Okay. In the strain hardening formulation, kappa increases or decreases with plastic strain. And again, we will more formally define what that means. Okay? The reason why 2 is so popular is because it's simple. Okay, that's one thing that is taking me many years to finally accept in life, is that simple things are more appreciated than complex or even elegant things. Okay, so be aware of that, even in your work. Okay, I think that the younger we are, the more we want to go for the complex, the sophisticated, the elegant. And then as we get older, we start migrating towards the simple, okay? There's a reason for that, okay? Work hardening. So how does it work? So work here is defined in the usual way. So if you look at your stress strain curve, say in 1D, just to make a cartoonish representation, this is delta epsilon. This is your value of your average value of sigma or whatever. This here, this chunk here can be called power, okay, which is typically defined as sigma times delta epsilon. Okay? And then you relate power, so the integral so that you take this P and you integrate it over the entire length of time. Okay, this will be what people essentially would call work in general. Okay. So P in 3D will be defined as sigma double contracted epsilon dot. Okay, and then if you take a look at this, then this becomes sigma. If you believe or if you adopt the additive decomposition as we do in plasticity, this is true, right? And then you hear people speak about something that we can call the elastic power, plus something that we can call the plastic power. Or, here I'm calling them, let me be consistent with my nomenclature. Let me call it PE. I'm sorry. I don't know why. I know why I'm doing W, but W is something else. So let's just call them PE and PP for plastic power, elastic power. Now, what I think makes, so sometimes you also hear people call them energies. So when you hear people talking about power, energy, work, you see a lot of these terms being used in all kinds of combinations, okay, depending on how people define things, okay? So sometimes you hear people call this also energy. Okay. So the part that makes this guy, so your work hardening formulations that relate to plastic work will emanate from here. And the issue with these, I think, is that if you look back at what sigma is in general, it's going to be something like this, right? Given what we know about Hooke's law, let's say this is linear elastic. So then you get a coupling between your elastic strains and your plastic strains. Okay, and this implies difficult. Okay, and you rarely see these formulations. But anyway, let's just finish what people do. So, plastic work is defined as the integral sigma double contracted epsilon dot E dt. So you take the integral of the power over time. Okay, and you get what we're going to define as plastic work. Okay, and then what people do is they make kappa a function of the evolution of that plastic work. So let's just rewind a second. So what people do is they compute in the plasticity model the increment of plastic strain. They double contract it with sigma. That gives them the plastic power, okay? Or the incremental work, if you want to see it like that, the increment of work. Then you add up as you proceed in the loading process. You keep adding how much incremental plastic work you've done. And what that value is at any time Tn or Tn plus 1, that you formulate a function of kappa that essentially evolves with Wp as it evolves. Okay? Very elegant, very nice, not so easy to implement, as you will see. Okay? This is difficult. So, makes sense. But this is complex. And you will see the world of a difference that strain hardening makes in the plasticity formulation. Okay, so every now and then you see people pushing in that direction, but it's kind of a moot point. I mean, everybody knows that it's great, but it's so difficult that I don't think it's ever going to catch on fire. But who knows? On the other hand, strain hardening, you'll see, it's a lot more intuitive. So here's what strain hardening does. So in strain hardening, you define some general plastic measure of strain, say C dot, that in this case, for instance, you could just make it equal to lambda dot. And you say, well, we know that lambda dot is always the norm of a plastic strain rate. So it's always positive, it's always nice. So I can define a measure of cumulative plastic strain just as the integral of whatever this measure of plastic strain is. In this case, okay, you can call this lambda, essentially. Right? So it's just your accumulation of plastic strain, regardless of whether you were positive, negative, it doesn't matter. The way we formulated it is blind to tension, compression. All it cares about is that you had a plastic process. The more plastic processes you have, the greater this number is going to be, period. Okay? Direction will be accounted for in another way, as you will see. So I can then make kappa simply a function of my accumulated plastic strains. So let's call this your cumulative value or magnitude of plastic strain. All right? So this is much more often used, and the reason why it is so is because it's convenient. Let me show you how convenient it is in the case of a J2 model. So let's apply this concept to isotropic hardening for the J2 model. So, as I told you before, what isotropic hardening means is that your plastic surface, your yield surface, grows or contracts equally in all directions. So in the case of a J2, you have an infinite cylinder, so its longitudinal direction is not going to change. It's infinite already. The only direction that can change is the radius, and the radius is controlled by what plastic internal variable? Kappa, okay? So in the case of isotropic hardening model, all we're going to do is we're going to evolve kappa. We're either going to make it bigger or smaller. And the way we're going to do it is in the standard strain hardening way. So here's how it goes. So recall that the consistency condition required the calculation of the evolution of F. And before, we had said that this was dF, the sigma, double contracted with sigma dot. This is true. And then by the chain rule, this is also true. But then we dropped this because kappa dot was 0 before, because kappa was a constant in the first version we saw of the model. At any rate, we require that that's equal to 0 always. Okay, so far so good, right? Then, by the concept of strain hardening, I'm going to write kappa dot such that I have some kappa prime. So I have some d kappa dc, right? I can formulate some function of kappa as a function of c. And then all I need to do is compute the time derivative of c. And that's equivalent to the time derivative of kappa. Yes? No? This we know is lambda dot as well. So I can write these as kappa prime, so the derivative of kappa with respect to its main variable, which in this case is the cumulative plastic strain, times some lambda dot. Okay, so then df d kappa, I can, let's just do df d sigma double contracted with sigma dot plus df, how does it go? D kappa, oh yeah, and then I replace this kappa dot with kappa prime lambda dot. And then, as a matter of convenience, I'm going to put a negative sign here. I'm going to put parentheses here, and I'm going to put another negative sign here. Okay. And I'm going to define this as a good old friend we used to call H. Remember H prime? Okay, it's very close relative is back. Now we call him H. So this whole thing becomes df d sigma double contracted with sigma dot minus h lambda dot has to be equal to 0. And we're going to baptize this guy as a hardening modulus. So check him out. H equals df d kappa kappa prime with a minus sign in front of it. In other words, you could also write it as minus df dc. Meaning it's a measure of, we're computing the variation of F to the accumulation of plastic strength. Okay? That's what this derivative means. That's what the hardening modulus is. How is F changing as I am accumulating plastic strengths? If it is positive, we will see later, we will call it hardening. If H is positive, we'll call it hardening. If it's negative, we'll call it softening. If it's 0, that means that F is not changing with plastic accumulation of strength. And then I must be perfect plasticity. Okay? So even though I'm accumulating plastic strength, my F is not changing. So I must be, my cylinder must be fixed in this case. Okay? So recall that. Make a note of that. So I arrive at one of the most classic versions of the consistency condition. I would say 95% of the models I know always have this form, okay? Or they can be written in this form. So your F dot is your variation of F with respect to sigma, and then the variation of sigma with respect to time, minus a measure of variation of the yield surface with respect to the plastic processes. And again, if you recall, sigma changes are related to elastic processes, as you might recall. So this is the nice division between elastic processes and plastic processes being detached, decoupled. Okay? So even though this might be changing, because your elasticity is changing or your elastic processes are changing, this doesn't have to be changing. Okay? They're decoupled. Great. So, okay, let's look at what that means in terms of geometrical representation. So if this is my elastic domain, so this is my F equals 0, this is my boundary, my yield surface. And we know dF, this sigma is essentially what we have been calling n hat, or the normal to the yield surface, right? And we're here at this point. And now we are looking at some random sigma dot. These two vectors, if we are in principal stress space, these are two vectors. And two vectors always span a plane. And on that plane, we can always define this angle between these two vectors. Call it theta. All right? So, let's look at the possibilities. Df d sigma, double contracted with sigma dot, according to my consistency condition, is always equal to h lambda dot. This guy is always positive, right? This guy, we don't know. All right, so, if these are vectors, this would be a dot product in vector world, right? That would make it a scalar product. This will be equal to the cosine of theta, the magnitude of df the sigma, right, times the magnitude of sigma dot. Yeah? Yes or no? Okay. These are all positive quantities. Yeah? So, the sine function of this scalar product is equal to the sine function of the cosine of this angle in between. Recall the cosine function. Cosine theta versus theta starts at 1, goes to 0 at pi over 2, right? Then it gets negative. Okay? So, as long as theta is acute, right, this inner product is positive. The moment these two guys are orthogonal, this inner product is 0. And the moment that the angle is obtuse, this inner product is negative. Okay? And furthermore, this happens to be also the sine of h. So, the sine of h dictates the angle in between the normal to the yield surface and the increment of the stress. Recall that in perfect plasticity, we had a restriction, right? Sigma dot had to be what? What was the only case we were allowing in perfect J2 plasticity? It was so long ago, we don't recall it. Yeah, it had to be orthogonal. So we were only allowing this kind of sigma dots, right, where this was orthogonal to the n hat. Right? So that was implying h equals 0. So this is a generalization of that case. Okay, so h greater than 0, we call this hardening. It implies acute angle theta, okay? So theta less than 0. H less than 0, we call it softening. This is an obtuse angle theta, meaning theta is greater than 90. And finally, H equals 0, perfect plasticity. So we go back to where we started. So think about it. Your yield surface defines the edge, the limit of your elastic domain. The only way that you can take a new So, and let's say this is your sigma n, and this is your, candidate sigma n plus 1, right? Because that's really what this sigma dot is. It takes you from some sigma n to some new sigma n plus 1, right? So the increment is the one that enables you to change state of stress. So you're proposing an increment in stress, and that increment in stress can only have an angle that is acute with respect to the normal if the yield surface would allow you to expand, let's say, to account for this new state of stress. That means that your hardening modulus needs to be positive so that your yield surface can expand. Otherwise, you cannot go to that new state of stress that would obviously push out of the current state of elasticity. Similarly, if you're in perfect plasticity, for instance, let's say this cannot change in size, that state of stress is not allowable. It will land you in a sigma n plus 1 that is unattainable. That is not allowable because your state of stress cannot grow. Your elasticity cannot grow to accommodate that state of stress. So what are the only increments in stress that you're allowed to in perfect plasticity? Those that are orthogonal to the yield surface. Now here I'm exaggerating, and it seems like this one would be outside, but when this is really incremental in the true way, this is infinitesimal really. So it really continues to be on the yield surface. Okay, and finally, if you have a retracting yield surface, that's a case that we haven't seen yet. That means an H less than 0, the only allowable states of stress are those that are on this side. If you imagine a tangent line going through this point, the only ones that are allowable to you are those that are inside of that tangent line. Right? For instance, something like this. Okay, it cannot even sustain one that is orthogonal with an H that is negative, because that would imply that you land on the surface right where it was before, and this surface is retracting. Okay? So your H will impose, the sign of your H will put a geometrical constraint as to where your stress can go, okay, relative to the yield surface. And this is the new definition, the more general definition of hardening versus softening in 3D, as opposed to the easy one-dimensional definition where, okay, if sigma is growing, well, it's just hardening. Now it's more complicated than that. It has to do with a geometrical implication on your incremental state of stress relative to the yield surface. It's not as easy as before. But it is controlled by the sign of H, remember it. Questions? Yes, sir.
So when you're at a plastic state, and let's say you have softening and you go to a trial state, can it be tricky to distinguish between an elastic step and a softening step?
So let's see. So if you go, if let's say you're here and you go to a trial state out here, and let's say you're softening. Is that your question?
So I was imagining if you're going to the left side of that line you drew, you could be ending up in a
plastic. If you're going to the interior.
Yeah, you can end up in a plastic state if you're up more, that'd be a state of softening, or you can end up in an elastic state.
So, okay, if you go in, you have two possibilities, right? You either land on a plastic state because your thing is retracting and you were always on the surface, like your surface is dragging you back, or you are decreasing faster than your surface, in which case then you're in an elastic unloading.
So
So
you-
elastic unloading is relative to the speed. You know, imagine this is the water in the ocean. You know, when the thing is retracting. Okay, so as the thing is retracting, if you run with it at the same pace, you're in a plastic state. If you're running faster than the retraction, then you're in an elastic state. You're not touching the surface. So the question here is, where is your point of stress at any time relative to the surface? If you're in a plastic state, you must be at the same place. If you're in an elastic state, you must be inside, right? And outside is not an option, ever, right? So you can have motions in this sense that are either plastic or elastic. The only way to differentiate them is, are you on the yield surface or are you inside the yield surface?
So go check the yield function.
You have to check the yield surface. But again,
So you-
a priori, you cannot just see and say, oh yeah, it's unloading, or oh yeah, it's plastic.
So you would check the yield surface before you updated with your before you updated it with the hardening.
That's right. I mean, you'll see that essentially all of your equations in the algorithms that we're going to design check your yield surface, your yield condition at time Tn plus 1. That's why it's important to do an implicit integration, because explicit methods, for instance, will rely a lot on what was at Tn. And that's great if your increments are incredibly small. But the moment that your increments are a little bigger, you can start having these issues that you're trying to, solve in your mind, which is, okay, am I being consistent with my plasticity rules? Am I following everything that I'm supposed to do? Am I satisfying all the conditions? And the answer is that in explicit methods, not always. But in implicit methods, you are guaranteed you will, as you would see. I mean, everything gets updated at the same time. Now, the price to pay for that is complexity of implementation, right? Because, yeah, you have to guarantee that everything is happening at the same time, right? Because the state of this surface, recall, is a state of the stress and the plasticity, right? And this is being affected, and that's being everything is being affected at the same time. At the same time, this new value depends on where this is. So it's a very complicated system of coupled equations, right? Nonlinear equations, and that's why you have to iterate and so on. So you start to see what the problem is. So the more complex your model is, the more difficult that will become. That's why some people give up. And they say, all right, screw that. I'm going to take a delta sigma that more or less is close to where it should be, okay? And okay, that has some value too. Okay. Good questions. Let's keep going. So again, you see that plasticity has these very deep roots in geometry. A lot of people that like plasticity like geometry. So look at uniaxial loading. And here I want to be very clear that uniaxial loading is not equivalent to uniaxial deformation. So sometimes in your computational assignment or in many things that you encounter, you will be asked to do or run a test under uniaxial loading. What that means is what we talked about before. It's a state of stress, say sigma, that looks like this, which is not equivalent. So this is uniaxial loading. Not equivalent to this. Okay? Which is uniaxial deformation. Okay? You can see that these will give rise to a state of strain that has, yes, 1 epsilon in that direction, but then 2 additional components due to the Poisson effect, right? Similarly, this guy will imply a state of stress that has a component in that direction, but also has 2 components in this direction, and so on. Okay? So don't confuse them. So sometimes when we say these, people implement these, okay? And then they don't understand why things are not matching and so on. Your one-dimensional plasticity model is set up in this frame of mind. Okay? All right. So if we compute the pressure here, this will be 1/3 of sigma, right? That's just 1/3 of a trace of this guy. And then if we compute the deviatoric portion of that, we have shown before that that's 2/3 minus 1/3 minus 1/3. Everybody else is 0. Okay? So you can see that this is what kind of loading? Remember the definition we said way back when? Radial. Okay? It's, you know, your S, you have a bunch of constants in the diagonal, and then they just depend on the sigma. And if this sigma originates at the hydrostatic axis, let's say sigma equals 0 at the beginning, then this is radial state of loading. Okay? Again, go back. Say sigma 1, sigma 2, sigma 3, where, along which line is this kind of loading? Can you tell me? Along sigma 1, right? It looks like this on this plane. Okay. And this is, according to Tresca, this is a tensile form. Right? So, let's keep going here. So that's that. Now, of course, the trace of S is 0. You can see it. Okay. Then df, this sigma, which we're calling n hat, which is S over its norm. Okay, we just take the norm of this, we normalize S by it, and I just want you to believe me. This is remember that was another statement I made, that radial loadings had constant n hats. Okay, you can see here that n hat is a constant. Okay, just a bunch of numbers. Okay, so constant, which is consistent with the radial loading definition. So, when you double contract n hat with sigma dot, which is, I'm just doing the double contraction of df this sigma with sigma dot, okay? For the case of uniaxial loading, what am I going to get? Well, the only component that in sigma dot that is non-zero is the 1,1 component. So that gets double contracted with these, right? And I get essentially 2/3 times square root of 2/3 or 3/3, right? And times sigma dot. So that gives me root 2/3 sigma dot. You see that? Yes, no, maybe? Are you okay? Okay. Now, at the same time, the whole point of this exercise we're going through is to show you a connection with the 1D model so that you can link it. So at the same time, we have the plastic strain rate is lambda dot times n hat, right? By definition, right? This is lambda dot df d sigma. So my plastic strain rate is lambda dot n hat, I just found it out, is root 3/2 times 2/3 minus 1/3 minus 1/3. Is that right? Right. So in the 1D uniaxial loading model, the only component of the plastic strain that exists when they speak of epsilon dot p, they're really thinking epsilon dot p 1,1. Okay? That's what the model means. Okay? In the uniaxial loading model, when the model says epsilon dot p, remember, it really implies component of plastic strain in direction of loading. Okay, in other words, in the direction of sigma. So in this case, we have chosen that direction to be sigma 1,1. Okay, it could be sigma 2,2, it could be sigma 3,3, it doesn't matter. Okay, you just have to be consistent. Yes, are you still with me? Okay, so given that, then in this particular case, this is lambda dot, again, root 2/3. Or in other words, lambda dot equals root 3/2 of epsilon dot p. So my plastic strain rate in the general three-dimensional framework has a one-to-one relationship to the one-dimensional uniaxial loading version. Okay? You'll see how we put all of this together. So, n hat equals, oh, by the way, this before, in the 1D case, this was just the magnitude of this. Now there's a scalar. There is a distortion factor. Okay. N hat double contracted with sigma, we said has to be, this is by consistency, remember this came from f dot equals 0. Okay, this is true. So we just computed the left-hand side. This is root 2/3 sigma dot equals h, the hardening modulus, times lambda dot, which is and these are the guys that appear in your 1D model. You see that? They are your one-dimensional sigma, good old friend sigma dot, and your good old friend epsilon dot p. Okay, but now they're playing a game here in our three-dimensional model. Okay? So when we move things around, we get that sigma dot equals 3/2 H epsilon dot P, don't we? Okay? And remember that in 1D, that had to be sigma y dot. Right? Any change in sigma y had to be a change in the yield, in the one-dimensional yield strength. And furthermore, that had to be equal to this. You recall that? Yes or no? Kind of? Yeah?
Is that still in 1D?
Well, in 1D we called it like this, so let's be consistent. Okay? For the isotropic hardening model. Right? So this gives us a relationship between the hardening modular. This is your classic modular. So in 1D, so in 3D, H equals 2/3 of H prime. Okay? Or vice versa. So, again, why do we go through this? Because this is an important exercise, because many times what you are going to be given is the result of a uniaxial loading test. And you will be asked to then implement a three-dimensional model like the J2 model, calibrated to fit these uniaxial loading test results. And so the ability for you to go back and forth and calibrate things according to what you get. For instance, take this. So in your assignment, it says that the tangent modulus of this J2 model is 0.1 of E. So remember that the tangent modulus ET was related to H prime. So if I know ET, I know H prime. If I know H prime, I know H. Okay? So there are ways to calibrate models like this that you need to start feeling comfortable with. Same with sigma y and its equivalence. I don't have it here, but there is a way to make kappa equivalent to sigma y. So if you know what sigma y is at any moment in time, you will know what kappa is at any moment in time. Okay? Again, it will follow a very similar path to the one we just followed here. In fact, can you tell me what the relationship between kappa and sigma should be? Or we should leave it for some other time? I'll leave it to you. But from everything we've written, you should be able to deduce them. Okay, the relationship between kappa and sigma. I think I'm going to stop there, because after this comes kinematic hardening, and that just takes, that's a whole different discussion. So pretty much you are set to go for this first part of the computational side. You should be able to implement this with a little bit of hand holding. So maybe by next class I'll start covering the computational aspects of these. If not, the Borja book has quite a bit of content along those lines, and also, Alex can help you quite a bit. But I think